Hey guys, welcome to System Design Fight Club. Today we are going to be covering a inventory system. It's just a system for tracking the count of an item in a inventory system. Before we get started, a quick call out is that if you have any ideas for future system design interview questions that I can cover in the future, there is a form in the description below that you can fill out and submit that idea, and I'd be happy to cover it in the future. With that, let's go ahead and get started. We are going to be designing a inventory tracking system. A very useful resource for figuring out how to do this was looking at how different payment gateways work, like the one for Stripe. I actually read through the documentation for Stripe for working on this problem and figuring out how to do it. That might be an interesting thing to look at for this, but you'll see why in a couple minutes, why that would be useful. So what are we going to be supporting here? We are going to show what items are actually in stock. We'll track the count of the inventory as it changes. So if you have 5 items, then you decrement it by 1 5 times, it will then become unavailable. So you have to have the actual count tracked at all times. The inventory change may occur in a distributed transaction that's being performed by other services. You could just directly expose your database that other services could go ahead and coordinate with your database directly and do their distributed transaction. But if you have dozens of clients, that is going to be that's a bad practice. It's bad practice to couple directly through a database. So instead, what we're going to want to do is expose an interface for these distributed transactions. That's where the payment gateway documentation came in handy, is that it's going to be very similar in appearance to how payment gateways set up their API. Another thing we're going to support is inventory snapshots and inventory auditing. So for example, all publicly traded companies on the stock market have to fill out a earnings report once a quarter. And one of the items you're going to find in that earnings report is actually the inventory. It's considered a part of the company's assets. I think it's short-term assets. And so they actually go over what all their inventory is, calculate up the cost and the value of all of it, and then that's actually an item in the 10K form. I think that's filed every quarter. So they're probably going to need some kind of snapshot that they would build that off of. What's going to be out of scope is going to be ordering itself. So the actual placement of orders and handling payments. That'll be a different service that will be handling distributed transactions that interface with our service. We're also not going to handle listings and location lookup. So this could very easily turn into one of those problems where a very closely related area is looking up a nearby store and like where you'll be able to get a specific item. So let's say that you're located in Seattle and you want to get and you're looking for a box of pencils. And so when you're trying to place an order for it, you would want to find the closest warehouse that has that box of pencils. Instead, a different service is going to be handling tracking the actual location of warehouses, and it'll find the ones that are nearby and can meet a certain shipping speed. So that's why you would need the location lookup, is that even though it might be shipped, you might want to have it shipped in under, let's say, 2 days. And if you want to have it shipped in under 2 days, you can't be getting a pencil box from China or Europe or Australia. That's why it would limit the number of warehouses you can ship from. So instead, we're going to have something else that'll filter to warehouses, and then we're just going to track the inventory of that specific warehouse. So we'll receive a list of warehouse IDs instead. And so the whole thing with quad trees or R trees or geohashes, that's going to be out of scope. A couple of call outs that we're going to cover is a lot of interviewers will like to ask they'll like to bug you about thread contention. That's definitely a tricky part of this problem that can definitely that's one of the things that interviewers like to bust your balls over is thread contention for the records. Another issue we might have is a large object issue. I'll describe that more as we get to it. You'll see what I mean later. Now let's go ahead and get into some numbers. So I'm just kind of going off of Amazon.com, and I found a bunch of numbers for Amazon.com itself, just on the internet, for what kind of volume they're getting for their services. And we're just kind of designing the inventory for basically Amazon.com is going to kind of be the basis of how we're designing this. So some numbers for that is they get about 3 billion visits a month and about 10 page views per visit. So a visit is not just one page load. It's like them doing their whole shopping process, possibly successful or unsuccessful, and fully converting to a purchase. Another important number is how many times they actually buy. So I looked at the Prime Day numbers for 2022. They actually sold 300 million items in about 2 days. I have some other important numbers here that are interesting. They could be useful for determining some skew for like a celebrity issue for some of the items. I know that that is definitely a thing that happens for Amazon, is that some items are a lot more popular than others. We're not really going to try and figure anything out there. It'll actually be, there's not actually any statistics out there that were really solid for overall skew. They had some numbers on some specific items that were particularly examples of a celebrity issue that's going to occur, but I don't want to get too much into that. Instead, we're going to focus on the distributed transactions for my coverage in this problem. Let's go ahead and calculate what kind of volume we're getting here. Okay, so we have how many reads, how many writes a read is going to occur with each page visit. We're going to say that there's going to be at least one product's going to show on every page visit. Sometimes the page visit might be on a list of items that it's showing, and so that might actually involve well, that would be a key range query. But we're going to say that each page view is going to be one read off the database. Okay, so 3 billion times 10 gets us 30 billion reads per month. We're going to do 30 billion divided by 30. That gets us 1 billion reads per day. And then 1 billion divided by 100K will get us reads per second. Okay, so 1 billion divided by 1,000 would be 1 million, and then divide by another 10 gets us to 100K. So it's going to be about 10,000 reads per second, which is pretty high. How many writes, how many items are actually getting sold, how many times we're going to be actually updating that database. For a nice rough estimate, we're going to be going off of this part right here. We have 300 million items over 2 days. So we're going to do 300 million divided by 2 equals 150 million items per day. How many items per second? 150 million divided by 100K. That comes out to 150 times 10. That is 1,500 items per second, which will be about 1,500 writes per second. Okay, we can go ahead and hop into doing the diagrams now. I guess first I might want to explain how we're going to make that interface for the distributed transactions. There's going to be 2 steps to it. You're going to be able to, one, place a hold on the item, just like put it in your cart on Amazon. And then 2 is you're going to execute hold, as in it's actually going to decrement from the inventory. That's going to, you'll see how that's going to shape the schema of our database here. So we're going to have a browser for the customer. We will have a backend service. Well, okay, so we're not going to actually interface directly with the customer. We would have maybe some kind of ordering service. ahead of it. It's there. Okay, and then ordering service will need to, well, so there's the ordering service for when you do the actual buying, and then there's the listing service for when they're just kind of checking out the page. This is when they actually click the buy button. Then we're going to have the listing service. So this one's going to do reads, but they are both going to interact with our inventory service. Okay, so I want to focus on the read scenario first, is that you've got a request coming in to the listing service, and it's going to want to see some inventory. That'll send a request over to us. We're going to have to check our inventory. We're going to have a database of the inventory. So this will be the inventory DB. Okay, and then it's going to make a call to the inventory DB. We're going to get a response back, and it'll send that over to the listing service. And then the customer will see what items are available. Okay, and then that's just for reading it. What about when they place the actual order? So now they want to place an actual order. You see the item they want. They click the buy button, or they've added it to their cart, or we're going to place a hold on the item. We have an item, they're placing it in the cart, we're going to hold it. So that comes into the inventory system. Hey, hold this item. Let's make this a little bit bigger. It's going to get a little bit more messy. Okay, and it's going to update the inventory. Now let's go ahead and dive into the schema a little bit. So we're gonna have a item ID. Let's justify it. Say it looks something like ABC 1, 2, 3. And have the actual count. Say that there's 5 items. We're gonna have the warehouse ID. There's an inventory. So Amazon has multiple warehouses, not just one big one. And like I said earlier, we're not going to do the actual location lookup of the items. We're not going to track where the warehouses actually are. It's going to have a filter already for when it's doing that read and lookup of the key range query for nearby items. It's going to pass in already a list of the warehouse IDs that we're going to filter to. So we're going to want to track the warehouse ID. We'll say this is warehouse number 123. Got 5 of this item at the warehouse. That's the count. And then when the second one comes in, we're going to want to do a hold. We're going to hold the item. And we are going to want to get a UUID for each hold. So when you place a hold on the item, you have a request for a certain item ID, and you're going to have the count that you want. So let's say they even want 2. They want item ABC 1, 2, 3. Oh, I had a typo. It's ABD. Let's do ABC. They want 2. And then in the response, you're going to have some kind of UUID. DEF, ABC, 1, 2, 3, DEF, ABC, some kind of UUID, and we're not going to bother with getting the details of how UUIDs work. That's like a system design problem of its own. We're just going to outsource that to a UUID generator service. So when this comes in, we're placing it in the cart. It's first going to get a UUID. Going to return the UUID, and we're going to use that for making the hold item. It's the hold it'll be for, we'll have a UUID to it. It's where we have this come in, have the UUID. We'll want the amount and we'll want a timestamp. Because what if they just have it in their cart indefinitely? How long are we going to let them hold it in their cart? So we want to reserve 2 items. We'll say 2 here, and we'll have a timestamp 137.005.123. So Unix epoch timestamp. I think it looks roughly like that. And when you add the hold, it'll also decrement this. So it's going to be a transaction, but it's a transaction on a single database. And so it's very easy to just, it's not a distributed transaction. You don't have to worry about coordinating it between multiple heterogeneous databases or different database instances. It's just a single database instance, maybe internally, and it does implement Paxos or Raft or something like that. But you don't have to worry about the actual details of it. It's kind of contained within a black box. So we originally had 5. And now we're going to use the markdown notation for crossing that out. It was 5. Now it's 3, and we have 2 there. And so you're going to do that within a transaction. It'll be like a compare and set thing first. So you do begin transaction. First thing you do, read off the current record for that item. Then you're going to modify it from what you've just read out by decrementing this by 2. You'll set that. You'll add this in here. And then you'll set it onto that record. You'll write it over top of it. It's a compare. You read and then you do the update. Yeah. Okay. So you've got the hold, and then you're going to return that UUID of the hold, and it's going to be successful to the ordering service. That's if it's successful. If it's not, so what if there's, a failure where you return the UID to the inventory service, but it fails to give it to the ordering service, then you're just going to have this thing, and that's where the timeout's going to have its effect on this system. Is we'll have something else that's going to clean out these holds after like 7 days or something like that. So it's the interface we're exposing is going to look a little bit like what's in a 3-phase commit, which is where there's a 3-phase commit differs from a 2-phase commit because it has a timeout that doesn't allow you to permanently lock the records. So after 7 days, if this is just kind of still sitting there because you didn't successfully return the UUID back from the inventory service to this, then it's just going to clean this back out and release the inventory in the hold back out to the overall count. Okay, so that was step 1, is you got the hold. What about step 2, which is when you actually execute the hold, when you've actually made the purchase? So I'm going to make a copy of this whole thing. We're going to copy and paste this whole thing. And we're going to talk about step 2 of the design. So listing service is no longer relevant. It's not really involved anymore. We don't need the UUID generator anymore because we've already got our UUID. So we've got the buy come into the ordering service or something. And they want to actually go ahead and make the actual change to the inventory. They're actually buying it. So we don't need the timeout anymore. We're going to actually execute the change. So for the executing of the hold, you can only execute it once. You can only execute it once. So here you're going to have the UUID in the request. And then you're just going to return a 200 successful response, which is just like, hey, yep, I flattened it. And for the first step, we are going to favor strong consistency. So that's why it has to be synchronous. However, here, it doesn't necessarily have to be strong consistency. We can actually err on the side of high availability instead. So when we add it to the cart, we really want strong consistency. They could get an error like, hey, I failed to place it in the cart, but here it's already reserved. We know we're going to be able to get it. So we can just go ahead and err on high availability because there's no risk of any kind of bad data transformations occurring from the result of having a little bit of staleness. It might just look like their cart was not actually successfully purchased for a few hundred milliseconds. Let's go and show how we're going to switch over to high availability here. So we've got our database that looks like this. And instead of talking directly to it, so the reason why I want high availability is that there's a couple of things I want to do here. So we can immediately add a message broker when we're not favoring strong consistency. You can't have a message broker when you need strong consistency because it immediately brings you down to eventual consistency. I actually have another video on that. It's titled something like why when you can't use message brokers, how message brokers break strong consistency or something like that. It's also a best practice to decouple your database from the rest of the system by having this by having a broker. It helps improve availability just in general, but you just can't have it when you have strong consistency. In particular, I want to have this decoupling here because we also want to do a second thing, which is we're going to capture it in an event sourcing thing for our snapshot, our snapshots for the 10K. We're going to use an event sourcing database for that. So we're going to do the buy. We're going to execute the hold. The customer says they want to execute the hold. They tell the ordering service. The inventory service says, hey, inventory service, go ahead and execute it. Now it's actually going to go over here to the message broker. I think I actually have a better icon for message broker. Oh no, that's right. I don't like these because they're wide. I didn't like that. And you're actually going to have some task runners over here. You can just use like a Lambda function. And for the stream, for the broker, it's going to be very high volume. Like I said, we have something like we can get about 1,500 writes per second. You don't really want to use a queue at that kind of volume. It's better to use a stream. So we might want to use something like Kafka. Okay, and then the task runner is going to pull it off of the stream, and it's going to do the compaction over here. So the inventory had 3 beforehand, and what it's going to do is it's just going to kind of delete this out of here. So it's just going to strike that out. It's going to go to empty. And we're also going to record this this change in the inventory also to a event sourcing thing. Over here, it's the event sourcing center that like that. So you might be wondering, why do we need an event sourcing DB? It's for rebuilding. It's for doing the snapshot at one particular point in time. So we're going to want to build a snapshot up to December 31st at 11:59 p.m. 9 p.m. On December 31st. But we have 350 million items, and so we're going to need to do, like, what are we going to do? A full table scan over here and like just lock the whole thing for that. Instead, you can use event sourcing, and then you can rebuild the database at any point in time instead of having to freeze the whole thing just in order to build your 10K report. It's if you freeze the whole thing while building the snapshot, you wouldn't be able to place any orders. And so then you would not be making revenue for that whole point in time. And then also it's decreased availability for your website. Which is a bad customer experience to begin with. You generally want your website to be as close as possible to 100% uptime, because otherwise people think that it's a crappy website. So it's good for your reputation. It also allows you to not lose any revenue off of dropped orders. Okay, so you're going to update the inventory DB, and you're also going to place the record into the event sourcing DB. And we're going to have a schema where it'll have, we want to have the item ID. We also want to have the UUID for each of the things in the event sourcing. That, we want to lab justify. So UUID, this is to make it item potent. So if there's a partial failure for the task runner where it completes this first one, but it fails to do the second one, actually, so you would want to do the event sourcing first. Otherwise, this might be, well, oh, the message would have the UUID. So the message coming in would have the UUID for what it wants to flatten. Okay. If you didn't have that, then you would need to write the event sourcing DB before you would delete the record. Otherwise, you would possibly lose that information before you'd be able to potentially capture in the event sourcing DB when a partial failure occurs. But we have it there, so I guess it doesn't really matter what order it actually happens in. Although I might want to update the inventory DB first. Just for the sake of consistency for other things. Well, it's already removed from the count. It really doesn't matter, I guess. You can just have these happening in either order. So you can even have two different task runners and you just have a pub sub thing running off of the message broker. Yeah, so you can even just do pub sub on both databases. And so we're actually just even going to do that. I have a second one. And we're just doing pub sub off of it. Just like that. And I'm drawing the arrows like this because it's doing a pull off of Kafka. Kafka does not push onto the task runners. It's the task runners that fetch the data from Kafka. And we're just doing pub sub. This one's just kind of flattening the holds so that they don't get released at the timestamp. And then this one's doing is just for rebuilding. It's just capturing over here in the event sourcing DB. Oh, what else do we need over here? We're going to want the item ID. I guess that would also need to be part of the message. Yeah. Because we're not tracking what record has the UUID. So we want the item ID of ABC 123. Actually, so our whole primary key is going to be made off of the item ID and the warehouse ID. So we're going to pass both of those in the message. So and we would need the UUID for the specific thing we're going to flatten. And so then we're going to need the entire primary key also over here for reconstructing the snapshots of the database. So we'd have the item ID of ABC 123, and we'd also have the warehouse ID of 123. And we would have the count, which is 2. It's a decrement of 2. Actually, I should specify that. So you can also increase the inventory. That's a different change that can occur. So I should actually clarify that. So this is reserving an amount. You can also add inventory to the warehouse. So that number can be either positive or negative. So we would want this to be negative. And then so on the other hand, you can also have, let's say we're restocking the database. And so then we would have another item that looks like, say they're adding 200 more of that item in. So you'd have something like this, it's adding 200 more in the stock. Well, this one is -2, it's removing 2. Because it's going to be directional with the value. Okay, so decrement by 2. And then when they're restocking, those events are also going to be over there. Okay. All right, so you have the event sourcing database. What about the actual snapshots? So we are the inventory system. It is within scope for us. We're going to be able to provide snapshots of what the inventory is at any point in time. So we will have a task runner, or it's just workers. It's going to be something like a MapReduce job. Let's talk about the technologies briefly. For the inventory DB, I'm leaning on DynamoDB. And for those that aren't intimately familiar with the details of it, they might be saying, well, strong consistency, how can you do it with DynamoDB? You can, there's strong read consistency, you can do that. I'll get into more details of it, but you can do stronger consistency with DynamoDB in addition to eventual consistency. And I think you can even specify it on the operation level instead of just on the instance level. So over here, you would be able to do a strong read consistency operation. While over here, you can just do an eventual, well, no, you would need to do a transaction. Both of these are going to need to be transactions. So you have strong consistency on both of those operations, but what you're exposing over here on the actual by click is actually eventual consistency. So although the operation is run with strong consistency over here in terms of what the task runner sees and how you're doing the operation, you need strong consistency on the transaction, but what this person actually sees is eventual consistency, because you're saying like, hey, yep, you bought it. And then it's not actually going to do the buy until the message is brought off of Kafka, because it just returns immediately, and then the actual message just sits there until it's brought off by the task runner, which could take a whole day if the task runner, if there's an outage, the task runner is just straight up down. Anyways, DynamoDB for these, and then for the event sourcing, it's going to be very write heavy, and then you'll occasionally have this really, really big read operation for reconstructing the snapshot. And so I'm feeling Cassandra, which uses an LSM tree. And then DynamoDB makes further sense over here because of the B tree, because it's going to be read heavy, but this one's going to be write heavy, and so Cassandra makes a lot of sense here. I guess for the snapshot reconstruction, you could actually go with eventual consistency. So this actually has tunable consistency, so it can actually specify the number of read nodes and write nodes for operations. And I guess I can go ahead and do that. We'll see if I have time to do that. But we're going to use Cassandra, and you can specify either strong consistency or eventual consistency. But we're going to have these workers that are going to read off of it, and they're going to construct a thing into a snapshot database. So we're going to have a snapshot. Okay, and for the schema for that, I think it could just be similar to the inventory DB, but it would not have the holds. It should be holds, plural, or yeah, for like multiple. While this one's not going to have the holds, but it'll have, interestingly enough, a timestamp for what you're building the snapshot up to. So we'll have that over here. And we'll have it like that. And then you actually just have the snapshot over. The timestamp will be over here. And so if you're building a snapshot between that first and second operation, you should be able to see 3 instead of 203. We'll say the second one happened at 6,000. So you're building a timestamp for 5,500. You're not going to have the holds. Let me update that information over here, as we're going to say this one is for 6,000. Okay. And so the worker is first going to read off the snapshot for the old snapshot, the most recently constructed one. And then it is going to take a whole bunch of events off of Cassandra from since that previous one's timestamp. So we would have, let's say the previous timestamp is for 4,500. So it would read off whatever the most recent timestamp is for a certain item ID. And then it would have the new timestamp that it's building it up to. And then after reading off everything from the event sourcing, it'll go ahead and start doing a write of the new ones. And this should be idempotent. It should be idempotent because it's going to reconstruct the same record every single time. So we're going to have one read hold snapshot. We're going to have two read events since the old snapshot. And then we're going to have 3 Well, so I mean, it's first going to generate the new snapshot. In the worker, and then it'll go ahead and start writing the new snapshot. And I think you can use something like MapReduce for the workers would work really well. So Amazon has EMR, for example. AWS has EMR, if that's what you're using. I tend to use AWS resources because I'm just most familiar with them. So MapReduce has really nice integrations with Cassandra. I would hope that EMR can similarly keep using those nice integrations that are normally provided through, if you're just using your own, if you've rolled your own data center, you would be able to leverage those nice integrations between Cassandra and MapReduce. I don't know how Cassandra would be offered in AWS through their services, but Cassandra just seems like the best choice here. So good luck with figuring that out on your own if you actually try that. But MapReduce would integrate nicely. I think that's the best way to go with that. And then you would have, you would not allow the end users to access the snapshot DB directly. So you would probably have a snapshot service, snapshot reading service. It will be the snapshot service. And I guess this one would, whoops, that was weird. Oh, I changed the font kind of. Okay, so the snapshot service is going to have a couple of operations to it. It's you're going to be able to, I guess you would even want to have a metadata DB, because the first thing that you're going to do is request a build of a snapshot, and then you can like it's going to take a while to generate the snapshot. It's going to take a while, so you can maybe monitor the status of the snapshot getting built, and then you would be able to download the snapshot off of that. So you would even possibly want to have a metadata snapshot, metadata DB. Okay. And then, so it writes the new snapshot. And then the fifth thing would be that it would mark the status as done. Okay, so schema for the snapshot, you would want to have a timestamp for the snapshot. So we're building one for 5500. So it's 137005500. And then we're going to have status. So there's requested, in progress, and you also have complete. Okay, so you have the snapshot service. You got a request come in for a new snapshot. First thing it does, create it, and then 2, go ahead and kick it off. So that's when you're requesting a new snapshot from the accounting department. Is first creates the metadata, and then it goes to the, well, I guess you could use a message broker, which would then be, so what if it does this and then it fails over here? So you would want to do this first, and then you would want to do that, so that it's idempotent. And what if you do first requested, and then you do that, and then you do 3, mark it as in progress, because you successfully started up the MapReduce job. I mean, I guess if you accidentally start up 2, you're just going to waste a couple of resources. They should both generate the same result over to here, and they're just going to be making the same record. So that's not the end of the world. That would be weird though. Yeah. Okay. So I can kind of annotate that as one, make new request and mark status as requested. Two, make the map reduce job. Three, mark request as in progress. Yeah, and you could even have like another thing that's checking for the partial failures, or you could have a message broker. I like the message broker that kind of would like drive it through. Otherwise you'd have the retries within the snapshot service itself, which is weird. Yeah, I guess I do kind of like that. There's probably a much more straightforward way to do that, but I have a lot more confidence in this approach, and I like when things are idempotent. To have a thing for this, and you would have the message broker. You just use SQS. It's going to be really low volume for the message broker. RabbitMQ is another option for that. So you request it, goes over to here. It's pulled off of the message broker onto this. You can just use Lambda functions. So it's task runner. You can do Lambda functions. There we go. Okay, and then you can also request the status of how your snapshot is. Is it done yet? So that would just be a read directly off of the snapshot DB. So due to the message broker, when you do the first request, if you somehow manage to try and do that within the first few hundred seconds, it might not show up, which will be weird. And then they'll refresh the page. It'll be like, oh, there it is. It's marked as requested or in progress. And then three, the third step when you're actually downloading the request will be off of that'll come from the snapshot DB itself for step three. So one, make a new request. That's this little part. Two, checking the status of your snapshot. That's through this. Three, download the actual snapshot. That's over here. Okay, a couple call outs. Thread contention and large objects. Let's do large objects first. So what if you have a whole bunch of holds over here on this thing? What if you have like 100 of them? Then DynamoDB can only support objects that are so large. So you can actually go ahead and have you could spin out the holds into its own database, the hold DB, and then you do your own distributed transaction against these two instances, and then you would expose that'd be within the exposed interface for the distributed transaction. So you'd have a distributed transaction within a distributed transaction. Sounds a little absurd, but if you want to have if you have that large object issue and you want to handle it, I think this would have to come out, that the holds part would have to come out and get flattened so that each hold is its own record over here. And then you would need to modify both of the databases with strong consistency, which requires a distributed transaction. So you'd have your own distributed transaction just within step one of doing the exposed interface. Thread contention, you are definitely going to get grilled on that by some interviewers. They love to be like, well, what if it's a Prime Day lightning deal, and the item is selling out within minutes or seconds or whatever, which means that you're going to be getting hundreds of requests per second for a single record. Yeah, that's some interviewers definitely love to grill you on that, particularly with Ticketmaster. If it's like a Kanye West, or it's a some musician has a performance, and the tickets just went live at like midnight or something, and the whole thing sold out by thanks to scalpers and shit within seconds. Thread contention is a concern. So I've got a couple of ideas for how to do that. One is that you just don't track the inventory. So then it becomes non-blocking. So when you do transactions normally, there's the thread contention is that the different requests are blocking each other. The transactions are blocking each other. And so some of them will start to time out or something because you just have like a case of like too many cooks in the kitchen. Thousands of requests in under a second for one record is going to be, you're going to have too many cooks in the kitchen. They can't all access the same record at once. So some of them are going to time out or something. I think that's usually how it manifests, is that some of the transactions or requests have too much latency from the first ones that managed to get into it. And so then it's the later ones, the unfortunate ones that are just a few milliseconds later will then time out. And so that's what the thread contention will look like. So one approach is just don't track the inventory. And so then you can oversell your inventory. You get a bunch of orders for inventory that's not actually there. So you're solving it by not tracking it when you're placing the orders. And then it's like you would have this task runner over here that's actually doing the executions, is where you find that, oh, hey, I have a hold that I'm trying to execute, and there's the count is now at 0. And so then you would somehow have to inform the thing that made the hold request that, like, hey, we have to cancel the order or whatever. So the one approach, don't track the inventory. That results in a lot of orders that cannot actually be fulfilled. Another approach is you can try sharding the item. So you can try sharding the item. So let's say that we had an item that has it has a count of, let's say, 5,000 in there. We have 5,000 items, and it's all in the one inventory. It's a really hot local item. Or even we have 5,000 in all the different warehouses that hold the item. And we're still getting it sold out within seconds in each of the warehouses. So what you could do is you could try sharding it out by doing something a little bit similar to consistent hashing, or how the celebrity issue is handled, where you have the item ID plus math.random between, like, 1 and 100. This is from DDIA for it's like in the little section on consistent hashing, is when you have a celebrity issue, you can shard it out. So you can actually try and do that with the item IDs. And so then when you have this come in, it's going to go to one random one of the records. So when you're doing the increase the inventory, you would also want to split that into multiple increases. You would scatter it over all the math.random or something like that. But then with the decrement, you could go ahead and have that you could go ahead and have that hit one record, while with the inventory refills, you would want to have that split in some way, or just go ahead and evenly distribute it across all the records. Another approach is you could place the orders, and then, so this would be similar to the non-blocking approach. It's where you place all the orders, and then you like assign which ones actually get inventory. That still is just roughly the non-blocking approach that I mentioned earlier. All right. I think we covered everything that I wanted. Another thing that I just don't really have time for is that, what if you're doing a warehouse audit of, like, hey, our system says that we have 5 items, but it's actually 3 because 2 of them got lost or stolen by our workers or something. Is you could have do rebuilds off the event sourcing for singular items. And then you would have a thing where it's like, hey, I'm checking the count in the warehouse. Here's the timestamp before I check the count, and here's the timestamp after I do the count. I got a count of 5. Let's see if that's actually possible by doing the rebuild from timestamp A to B. So you'd take 2 snapshots. You'd be looking at one specific item from the snapshot. So you'd build a snapshot for right before doing the count of the item, in a snapshot for when you're back. You're like, yep, finished counting it. Here's the timestamp for when I'm back at my desk. And then you have your count that you had, and you'll check if because orders might still be coming in as you're doing the audit of that item in the warehouse. And so you just check that count actually occurs between timestamp 1 and 2. All right, I think I've covered everything now. I did thread contention, I did large objects. Yeah, I think we're good. Thanks for listening. And again, if you have any ideas for future problems I can cover, I'm worried I'll eventually run out, so please submit them. I've got a link in the comments to a Google Forms thing. Yeah, I'd really appreciate it. Thanks again for joining. See you next time. Bye.